Let's see what's going on here. A drug is introduced into a patient's bloodstream by a bolus injection at time equals 0. X1 of t represents the concentration of the drug in the patient's blood, and X2 of t represents the concentration in the soft tissue. So typically what we're going to do is we're going to make a little compartment model, meaning we're going to have little boxes, and that's going to be X1 of t, and over here, X2 of t. And again, X1 is what's in the blood, X2 is what's in the soft tissue. So blood, soft tissue. Then we have to assume a few things. Well, they tell us. The rate that the drug is lost from the blood and excreted in the urine is X1 of t. So we're losing from the blood, and it's not going into the soft tissue, right? It's just going out of the body. So out of the body, we're losing blood at a rate of 1 times X1 of t. What times is X1? The rate at which the drug is absorbed from the blood by the tissue is 4 times X1. So from the blood to the tissue is 4 times X1. The rate at which the drug is reabsorbed from the tissue by the blood, so from the tissue to the blood, is 1 times X2. And finally, the rate of the drug lost to the sweat from the tissue is X2. This is a pretty typical diagram for a compartment model, where you have exchange between the two compartments, and then both compartments are also losing stuff because they are. I'm not great with the biology part of this, perfectly fine with the math part of this. Sometimes you also have stuff like going in, because like if you're talking about drugs, you're like introducing a drug into the blood. I don't think that comes up in any of these homework questions, but that doesn't mean it's not a thing. So after this, we're going to write a system of differential equations that model the drug concentration dynamics. And all we're going to do is just talk about what's going in and out of each one. So for the rate of change of X1, let's look at the arrows pointing into it. So into it, you've just got X2. Great. I'm going to write this kind of backwards for a second, but that's fine. So I'm just going to do the in and the outs. So into it, you've got X2. That's the in part. And out of it, which we're going to subtract, we're going to have 4x1 and also x1. If I was actually writing this differential equation in the standard sort of way, I would write this as dx1 dt equal to negative 5x1 plus x2. Because we always write x1 first and x2 second. And if I was going to try and solve this system using eigenvalues, eigenvectors, etc., I would need to write this in the standard way so I could write the matrix the correct way. Similarly, dx2 dt, let's see, what's going into x2? Well, 4x1 is going in, and that's it. So we've got 4x1 going in. Out of it, I have x2 and another x2. And then writing this in the standard way, I would write it as dx2 dt equal to 4x1 minus 2x2. But it's a pretty straight shot to write your system of differential equations once you have the picture. Look at what's going in, that gets added. Look at what's going out, that gets subtracted. And then combine whichever variables you need to combine to make it into a nice single kind of equation. Questions about any of that? Cool. I will say this next homework assignment, these first 3 problems should be pretty fast, right? They don't seem too hard. The 4th problem, we'll talk about that. 4th and 5th problems are pretty similar, and then we'll talk about problem 6 as well. Yeah, this next homework assignment, you can probably bang out like an hour or less, I would think. Maybe not. The last problem just gets a little more effort, but the first 5 problems should be pretty straightforward. Let's go ahead and look at the second part of this. So now we're kind of going the other direction. They're giving us the differential equations, and they're asking to set up the compartment model. So let X1 and X2 be concentrations of a drug in cell 1 and cell 2 respectively. So we've got cell 1 and cell 2. The dynamics of X1 and X2 are as follows. So we can see that out of X1, we have a 2 times X1. And also an X2. Interesting. Oh no, so we're adding in an X2. And then, yeah. And then similarly, going into X2 is a 0.2 times X1, and out of X2 is an X2. It's interesting. So the hard part for me about this is they didn't tell us all the errors we have, but if we just think about what's going on here, I know that coming into cell 1, which is X1, I need 1 times X2. Well, the only way to get that is to have it come from X2. Like that. And then similarly, X1 is losing 0.2 times X1, but it can't be going down there because since X2 is getting 0.2 times X1, we have to be going that way. So there isn't anything going out like from the bottom. We just have pure exchange, no loss essentially, which seems unlikely, but that's the way the problem was set up. Steady states. What does steady state even mean? Good question. So the steady state, just like we've been seeing for a while, is just another way of saying equilibrium. When are things not changing? And for systems like this, it's almost always just going to be when both things are 0. So the steady state, singular. No, I lied. That's not. So I didn't lie. I just didn't realize the weight. So that we have more than one solution here. So if we try to think about setting both negative 0.2 times X1 plus X2 equal to 0 and positive 0.2 times X1 minus X2 equal to 0, we might recognize that those are essentially the same equation. I mean, they're the same, just one's multiplied by -1 to get to the other one. So if I say solve for X2 here, I get X2 equal to 0.2 times X1. Or if you prefer, X2 equal to 1/5 times X1. So really, any situation where the amount of X2 is 1/5 the amount of X1 is a steady state. So really here, it's kind of like our eigenvector. Eigenvector? Yeah, it's an eigenvector. It's something like, instead of picking 1 and 1/5, 1 for X1 and 1/5 for X2, I'm going to pick 5 for X1 and 1 for X2. This is our steady state where X1, X2 is equal to any, say, multiple of 5, 1. Because as long as X1 is 5 times as much as X2, both of these dx, no, I didn't know. Both of these dx1 dt's and dx2 dt's will equal 0. Just to put some numbers in there, for example, if I pick X1 equal to 15 and X2 equal to 3, does that work? Yeah, it works. If I plug in 15 here, I get 0.2 times 15, which is 3, minus 3, that's 0. If I plug in 15 here and 3 here, I also get -3 plus 3, which is 0. That's what a steady state is, just where it's equal to 0. Most of the time for the usual system of differential equations we deal with is only going to be the origin. But occasionally you have something weird. Occasionally you have a case where the eigenvalue is 0. If we actually found the eigenvalues of this matrix, 0 would be one of the eigenvalues. And if 0 is one of the eigenvalues, it means you have more than one equilibrium. You have like a whole line's worth of equilibriums. So if we were kind of, yeah, I think it's worth actually looking at the graph of this just so you also can see what's happening here. So I'll point out that, and actually I'm going to show you what the actual graph looks like. I'm not just going to draw. I'm going to show you the real graph. But I want to point out here, like, if we look at this thing for a second, do I really want to even try and graph it? Not really. I mean, I could, but I have to find all the eigenvalues and the eigenvectors. Let's just pull up the graph. Let's see the real deal here. Except I didn't come prepared to do that because I wasn't thinking ahead. Where's my, oh, why am I need to make that tab or that bookmark be like closer to the middle. Direction fields. Yeah, cool. Oh, let me make sure that the people at home can see what I'm sharing. Should be sharing my whole screen, not just the visualizer. So if we put those just equations into, that's not the right one. Sorry, I'm all over the place. I want not the direction field explorer. I want the phase plane plotter. That's what I want. So we had dx dt equal to negative 0.2x plus y. And then the other one is just the opposite, positive 0.2 x minus y. If you graph that, it's super funky. So, right, all of your things kind of look like this. And the reason why that is because your eigenvector is the vector 5, 1. So essentially what's happening here is, here's your, oh, sorry, I keep trying to show you things that you can't see. So your one of your eigenvectors looks like this, over 5 and up 1, and it's got an eigenvalue of 0, so you're not pointing inwards or outwards. And then your other eigenvector, I was hoping not to have to find the other eigenvector, but I guess we have to find it. Let's find the other eigenvector real quick. Let's find both the eigenvectors. I know. Nobody's favorite thing to do. I will just mention, not that it's probably not going to come up, but I will mention that when you have a 2x2 matrix like this and one row is a multiple of the other row, it means lambda equals 0 is always going to be an eigenvalue. It's just a thing that happens with matrices. But if we try and find the eigenvalues, negative 0.2 minus lambda, 1, 0.2, negative 1 minus lambda, and we multiply this whole thing out, fractions, negative 0.2 minus lambda, negative 1 minus lambda, we have to say determinant there, minus 1 times 0.2, and if we do the whole thing here, I get a lambda squared, I get a plus lambda and a plus 0.2 lambda, so a plus 1.2 lambda, and then a minus is a plus 0.2, minus 0.2, those cancel. So you end up getting lambda times lambda plus 1.2 equal to 0. So your other eigenvalue is negative 1.2. If we try and find the eigenvector, we subtract that. So we do negative 0.2 minus negative 1.2, 1, 0.2, negative 1 minus negative 1.2. I know it's a lot of work here. So let's see. If we do that, that's going to be plus. So you end up getting a 1, 1 and a 0.2, 0.2. So your other eigenvector is going to be 1, negative 1. So my other eigenvector goes this way. So what happens is if you start anywhere, except it's it's not here. I'm saying, but like that's why you don't draw the arrows at the end of your lines, because this eigenvalue was a negative eigenvalue, which means everything should be pointing inwards, not outwards. So basically the idea is if you start here, you get pushed that way. And if you start here, you get pushed in the direction that is exactly parallel to that eigenvector that comes with an eigenvalue that's negative. So you have all these equilibria along this line, right? Like 5, 1 or 10, 2 or whatever. So that's what's happening in this situation. And whenever you have lambda equal to 0 as an eigenvalue, you do get more than one equilibrium. Just kind of a funky situation. You probably shouldn't worry about it too much. Okay. Questions? Questions about anything I've said there? Okay. Let's look at something like that. So let's continue on. I need more paper. Not use my spot here. Again, steady state just means generally kind of equilibrium, but you could have more than one if you have a lambda equals 0 situation, which in a lot of these problems with these diagrams kind of do. Let's look at something like this. Let's say we have the system of differential equations. And it's going to be, yeah, okay, sure. So it's going to be another one of these kind of things where dx dt is equal to negative 1.6 x plus 2.1 y. And dy dt is literally like the opposite of that. It's equal to positive 1.6 x minus 2.1 y. And we're told that this system of differential equations corresponds to the following compartment diagram. X, Y, and you have something coming out of X. You have A times X going into Y. You have something coming out of Y, B times Y going to X. And then you also have something coming out of X, so C times X, and something coming out of Y, so D times Y. And our job is to find out what A, B, C, and D are. And there's probably a way you could memorize the formulas for this. You should not memorize the formulas for this. It's easier just to do the work. I couldn't even begin to tell you. That's not true. I could probably try to tell you, but like, don't memorize these. Don't spend that memory you have on that. There's better places to spend your memory. So let's just write out the differential equations in terms of the ins and outs. So I know that dx dt should equal, let's see, what's going in? B times y. So I get B times y. What's going out? A plus C times X. Cool. Similarly, for dy dt, what's going in? It looks like A times X. What's going out? B plus D times Y. And so now I could probably rewrite these if I really wanted to. This is the same as negative A plus C times X plus BY. This one's already written in the kind of the standard way. AX minus B plus D times Y. And now just match things up and make the easy choices first. This is supposed to equal negative 1.6x plus 2.1y. This is supposed to equal positive 1.6x minus 2.1y. So it seems pretty clear to me that B has to equal 2.1. There is no other choice. And similarly, A has to equal 1.6. So those are the easy ones we can always kind of get first. We know that A is going to be 1.6, B is going to be 2.1. And then A plus C has to equal 1.6. That's annoying. Yeah. Oh yeah, of course, James. I'm saying of course. I'll tell you why I'm saying of course in a second, because there's something I'm seeing here that will be clear in a moment. So if A plus C has to equal 1.6, but we know that A is 1.6, then that's going to mean that C is equal to 0. And I think similarly, we will get D equal to 0 because B plus D has to equal 2.1. But we know that B is equal to 2.1, which means that D is going to equal 0. Why am I getting zeros there when they gave me things that didn't look like they should have been 0? Well, it's for literally the same reason as what we did before, right? In this previous example that we did, right? We started off with something that didn't have any outward movement, and our differential equations were exactly ones that looked like this, where they're the opposite of each other. Sorry, you can't quite see that. Like that. So when you have this sort of situation where, I don't know how to say it better than just saying like the amount of, right? You couldn't really have anything coming out of here because the amount of stuff coming out of X has to be exactly the same amount of X that's going into Y. And the amount of stuff that's coming out of Y has to be exactly the same amount of stuff that's coming into X. So there isn't any room for extra stuff happening here. Let's do a different problem to see how this changes, because it definitely gets more interesting. Assuming that, no, yeah, okay, good. I was like, assuming that we're doing other stuff. The thing I want to emphasize, though, is that the algebra of these problems is not hard. I mean, it's really just like solving for a couple things with doing a little bit of addition or subtraction. Well, let's look at one more example, and then we'll talk about a gap dynamics problem. So let's say we have another situation. So similar situation. But now we're going to say, sure, that dx dt is equal to, I'm worried about making the numbers wrong. Let's say negative 2.5 x plus 1.2 y, and dy dt is equal to 1.5 x minus 1.3. That seems dicey there, James. Y. And again, the same idea. This is representative of or corresponds to the compartment model. That's the same kind of thing. And definitely that labeling that we did previously is pretty typical. That's X and that's Y. Whatever is going out of X is A times X. Whatever going out of Y is B times Y. Whatever is going out of X sorry, I should have said whatever going out of X and into Y is A times X. Whatever is going from Y to X is B times Y. Whatever is just going out of X is C times X. Whatever is going just out of Y is D times Y. It's a pretty standard situation. So we know that this should be the same as dx dt equal to, let's try and be smart and write it in the normal order just to the get-go. So the stuff that has x's that's going into or out of X is, well, out of X we're losing an A times X and a C times X. So you have a negative A plus C times X. Coming into X, we have a B times Y. And then similarly, dy dt coming in, the X is concerned with this. We're having an AX coming in, and we're losing a B times Y and a D times Y. And then we do the same thing we did last time, except we're going to get slightly more interesting answers. So I'm first going to think about the things that are easy. The B times Y is easy. The B has to be 1.2. And the A times X is easy. A has to be 1.5. Cool. So A equals 1.5. B equals 1.2. And then we can find C and D by looking at what's going on with the other two parts. So we know that A plus C has to be 2.5. Since A is 1.5, we know that 1.5 plus C has to be 2.5. So C has to equal 1. All right, you all should find D. I'll give you a whole minute to find D. And know you can do it. Almost a minute, almost a minute, almost a minute. Okay. So to find D, I'm going to say that B plus D equals 1.3. B plus D equals 1.3. Since B is 1.2, we know that D has to equal 1.3 minus 1.2. So D is equal to 0.1. That's it. No one's asking us to solve, right? So after this, you could be potentially asked to then like find the solution to the system, right? Find the eigenvalues, find the eigenvectors. They'd be pretty ugly, not so much ugly, but the decimals make it less nice. So you have decimals where if I would, so just not that we're actually going to finish this, but if someone said to find the solution here and find the eigenvalues and eigenvectors, here, let me point out one thing you could do to make life a tiny bit easier. You can't go ahead and multiply this matrix by stuff at the get-go, but let me just show you what I mean. Let's say I was trying to solve the determinant of A minus lambda I equal to 0. So I would do the multiplication. I say, okay, I have negative 2.5 minus lambda times negative 1.3 minus lambda minus 1.2 times 1.5 equal to 0. And what I would probably actually do is multiply the entire equation by 10 twice. I would multiply this by 10 and this by 10. It's totally okay to multiply an entire equation by a constant. So if I do that, now I have the equation negative 25 minus 10 lambda times negative 13 minus 10 lambda minus 12 times 15 equal to 0. I'm not saying it's like 1,000% better, but it's a little bit better not to have to deal with all those decimals, at least in my head. So if I was multiplying this out, it's going to be 100 lambda squared plus 130 plus 250, which is plus 380 lambda. And then 25 times 13 is 325. And 12 times 15 is 180. And if you really want to, after that, you could divide by 100 again to make it the decimal, to go back to where you were if that felt better to you. If you thought, if it felt like better to use the quadratic formula that way. Again, I don't think you're going to have to solve something like this, but if you had to, this is a way you could make it a little bit easier to solve if you didn't have a calculator to use. I'm not going to solve, but you could solve it this way, right? I mean, yeah. That's all I want to say. Is that all I want to say? Yeah, that's all I want to say. Okay. Yeah. Okay. Let's look at a similar situation, but with more words. Let's look at some gap dynamics, which sure is a biology example. Gap dynamics. What are gap dynamics? Well, yeah, gap dynamics. A forest has areas occupied by gaps and areas occupied by adult trees. And it's either one or the other, right? There's either adult trees there or there aren't adult trees there. And if there aren't adult trees, even though there might be other vegetation, we're going to call that a gap. These areas are constantly changing. And that's the key word, changing, right? Things are changing, then we know we're going to have some differential equations. But let's say that G of T is the area occupied by gaps. I don't need to write it, but it's certainly implied the area occupied by gaps at time t. That's why we're writing G as a function of t. Similarly, we'll say that A of t is the area occupied by adult trees. Typically in these sort of problems, the assumption is you've got some finite amount of area you're looking at. Like maybe you're looking at 30 acres of forest. And you're saying, okay, well, it's either covered in adult trees or it's covered in gaps. But the total amount of area is never going to be changing. So it's always safe to assume in these problems that A of t plus G of t is going to be a constant. We'll talk about that a little bit more as we go. So let's say we have the following differential equations. We're given that dg, dt is equal to negative 0.2 g plus 0.1 a. Here's that something here. Yeah. And dA dt equals 0.2 g minus 0.1 a. Let me ask you all a question. If I was going to find the matrix for this system and find the eigenvalues, which I think I might actually end up doing here, can you tell me what one of the eigenvalues is going to be? Yeah. And we know 0 is going to be an eigenvalue because those equations are multiples of each other. That's how we know. Well, that's one way of knowing. Which kind of is funny to me because I definitely remember reading in her notes a few days ago, like that she said 0 wouldn't normally be an eigenvalue. Yet here we have many examples, right? There's literally a homework problem like this in there's at least 2 homework problems here, at least, where you have 0 that would be an eigenvalue if you were to find the eigenvalues. And yeah, definitely for this one, you will have to find the eigenvalues because they're asking you to solve the system. So, all right. Cool. So let's draw the compartment model. I would like you all to draw the compartment model. So I'll give you your G and your A. You got to draw some arrows. You definitely have arrows going across. You might have arrows going down. You might not. I like this problem. This is a good problem. Problem is, I didn't come with this problem. It's set up very well. I will admit, I think it's funny in web work. In this problem, in the similar problem in web work here, it says on paper, draw the corresponding compartment diagram. I mean, yeah. There's probably a way they could like have you fill it in, but like. So it certainly looks to me that out of G and into A, we have to have 0.2 times G. And out of A and into G, we have to have 0.1 times A. And that kind of takes care of everything, right? I can't have anything else coming out of G because everything coming out of G is the 0.2 times G. And I can't have anything else coming out of A for the same reason. And that's pretty typical of these gap dynamic problems. You don't usually have anything, right? Because again, we're not losing stuff to outside the system because we're talking about kind of a closed some amount of area. All right. I guess I'm gonna call that part A. So part B here, which I think is a good question. I'm a fan of this next question. Show that G of t plus A of t is constant. Which again, we've certainly said, right? I've said it probably at least 3 times that, oh yeah, it makes sense that the amount of gap plus the amount of area doesn't change in total, right? Maybe some days you have like, not days, it's probably over the course of time, whatever. But like sometimes you might have a lot more gap, sometimes you might have a lot more area, but every day you always have the same total amount of gap plus area. Okay, thinking back to maybe, I don't know, 17a, how would you show a function is constant? Or if a function is constant, what do we know is true about its derivative? Exactly. The first derivative has to equal 0. Great. So let's take the derivative. So the derivative of G of t plus A of t is equal to dg dt plus dA dt, right? You just take the derivative. But look, dg dt is equal to that. It's going to equal negative 0.2 g plus 0.1 a, and dA dt is equal to that, 0.2 g minus 0.1 a. And oh yeah, if we add those together, we're definitely going to get 0. So to show something's constant, all we had to show was that g prime plus a prime was equal to 0, which it definitely was. I feel like no. I've been touting how great that. I feel like this next question is actually not that great, but we'll talk about it for a second anyway. Suppose that we are given that g of 0 plus a of 0 is equal to 20. So the amount of gap at time 0 plus the amount of area occupied by adult trees at time 0 is equal to 20. I like acres. Let's say acres. Use part B to explain why then. I don't even think we need to do any explaining really, but we'll say. Use part B to explain why g of t plus a of t equals 20 for any t. Well, we just said that g of t plus a of t is constant. So if g of 0 plus a of 0 is 20, that's the constant value it's equal to. It can't change. So I don't think there's much explaining we have to do here. C part B. G of t plus a of t is constant. And we were just told it's 20. Okay. So now, given that g of 0 is equal to 2, so the amount of gap at time 0 is 2 acres, let's solve the system. That is interesting. I mean, yeah. I'm trying to think about how you might want to solve. I'm trying to think about how you would solve this and not do all the work in the world. Because we could definitely do this, what might feel like the typical way. Meaning we've got our matrix that we can write and find the eigenvalues and eigenvectors. But I should point something out. So, yeah. We can write our differential equations. Sorry, I lost them here. 1 second. Our differential equations. dg dt equal to negative 0.2 g plus 0.1 times a. We could replace a. Well, a of t is equal to 20 minus g of t. So we could use that to say this is equal to negative 0.2 g plus 0.1 times 20 minus g, which is equal to negative 0.2 g. 0.1 times 20 is 2 minus 0.1 times g. So we can rewrite this equation here as dg dt is equal to, sorry, I lost it here, negative 0.3 times g plus 2. And then we could, instead of do, oh, sorry, question. Sure, a of 0 does equal 18. Yes, that is also true.
Yeah, so.
But the thing is, this isn't a of 0, this is a of t.
Oh.
And then in a similar way, we could find that dA dt equaling positive 0.2 times g minus 0.1 times a. Well, we could actually don't even think I need to do all that, but I'm going to anyway because I just started doing it. Let me think. No, yeah, I'm gonna kind of, we could solve this, but we're not going to. So wait on this. Here's the point. We could do it the eigenvalue, eigenvector way, but we don't have to do all that because this right here That's a separable differential equation. So let's do it that way. I know it's been a little while, not that long, a little while though. So we do it that way. We're going to say, well, dg dt equal to negative 0.3 g plus 2 becomes dg divided by negative 0.3 plus 2. Sorry, 0.3 g. It's important. And that's equal to 1 times dt. And then we can integrate both sides. The negative 0.3 is kind of funky, but it's fine. Integrating this, we get the natural log of negative 0.3 g plus 2 divided by negative 0.3 equal to t plus a constant. And then I'd multiply both sides by negative 0.3. So I'm going to say that the natural log of the absolute value of negative 0.3 g plus 2 is equal to negative 0.3 times t plus c. We'll remind everybody that we have the initial condition that g of 0 is equal to 2. So eventually we're going to have to plug that in and figure out what c is going to be. Now might be my moment. I never know when the right moment is. Let's not do it now. We're going to e both sides. We're going to conspicuously drop the absolute value because we don't really want to deal with it. So we're going to have negative 0.3 times g plus 2 equal to e to the negative 0.3 t times e to the negative 0.3 c. And we're just going to call that a new constant. Let's call it a. Some people call it c. I like to call it a. So now we've got negative 0.3 g equal to negative 2 plus a times e to the negative 0.3 t. And then instead of dividing by negative 0.3, let's say that negative 0.3 is negative 3/10. So we can multiply both sides by negative 10/3 just to make it look not quite so heinous. So g of t is going to be negative 10/3 times, I'm going to write this as a e to the negative 0.3 t minus 2. And then we can plug in and find our a value. So we plug in g of 0, that's going to equal 2, and it's going to equal negative 10/3 times a times e to the 0 is just 1 minus 2. So solving for a here, I'm going to get, I probably should solve for a up there. Oh, well, I picked my moment wrong. Not that wrong. So let's see, I'm going to have negative 6/10 equal to a minus 2. So a is going to equal 2 minus 3/5, which is what? 7/5 or 1.4. 7/5? Seems like I'm doing something stupid here. Am I doing something stupid here? No, I don't think so. Sorry, one second. Let me just make sure I'm not doing something totally dumb. Oh, yeah, sure. Yeah, that's fine. I saw this notes I have did this a slightly different way, which is why I was like, that looks totally wrong, but it's fine. I did something slightly different. So our solution here, of course, I've run out of words, is that g of t is equal to negative 10/3 times 7/5 e to the negative 0.3 t minus 2. Or if you prefer to distribute the negative 10/3, g of t is equal to 10 divided by 5 is 2. 2 times 7 is 14. So negative 14 thirds e to the negative 0.3 t plus 20 thirds. There's something weird that I am not seeing here that's bothering me. Sorry. Seems wrong. Oh no, I'm not wrong. I see what's happening here. Sorry, sorry, this reminded me of a lyric from a song I've been singing in my head all day, which is from Moana. I see what's happening. Okay, anyway. Not at all germane to what's going on here. This is correct. There's a mistake over here. Cool. Yeah, is that cool? Yeah, that's cool. Yeah. All right. So here's the wonderful thing about this. You don't have to do any work to find A of t. Because we know, this is where things are beautiful. We know that A of t plus G of t is equal to 20. So then A of t, the amount of acreage of adult trees, is just 20 minus G of t. And then you can just slot that in right there and say that A of t is 20 minus negative 14 thirds e to the negative 0.3 t plus 20 thirds. And if you want to make it look a little bit nicer, that's going to be positive 14 thirds e to the negative 0.3 t. And then 20 minus 20 thirds is 40 thirds. So that's why I was saying we shouldn't even bother writing the A of t on the previous part, because it was going to be super easy to find it once we found G of t. And this is the way I would probably recommend doing this, even though it feels a little bit messy. It's probably easier than doing the whole eigenvalue, eigenvectors. I don't know, it might not be. We could do it the other way to see if you all wanted to, but I don't imagine you all really want to. Especially because, no, I mean, the eigenvalues shouldn't be terrible, but the eigenvalue should be negative 3 and 0. Because our solution looks like e to the lambda 1 times t plus something times e to the lambda 2 times t. Kind of neat. All right. Oh yeah, we should answer this last question here. And I really, yeah. I'm sure that's just a mistake. I'm gonna have to. I need to talk to Grant because I think there's a mistake on his hand here that I should help him correct, because, yeah, not over here. So then typically the last kind of question we usually ask for this kind of thing is, what fraction of the forest is occupied by adult trees? So, using so much paper. So at time t, what fraction of the forest is occupied by adult trees? Well, it's not too terrible. The fraction of adult trees is just A of t over the total amount of space, which is A of t plus G of t. But we know that A of t plus G of t is just 20. So we're really going to have whatever A of t was divided by 20. And so we look back at that, looking back at what our A of t was, that's going to be 1/20th times, here's A of t, 14 thirds e to the negative 0.3 t plus 40 thirds. And you can multiply that through if you really wanted to, but I don't think we really want to, because that's not the question that we actually really care about. The question that we actually care about is, as time goes on, let me phrase this the right way, meaning as t goes to infinity, what happens to the fraction of adult trees in the forest? Well, if we let time go on and on and on and on and on, what's going to happen to this part right here? What happens to e to the negative something times t? Does it go to 0 or does it go to infinity? goes to 0. Right, either the negative infinity goes to 0. So that part goes to 0, and you're left with 1/20 of 40 thirds, which is 2/3. So essentially, the stable equilibrium here, or the steady state, is where the fraction of adult trees in the forest is 2/3, and the fraction of gap in the forest is 1/3. And if you went back and did this the other way, where you found the eigenvalues, the eigenvector you would have gotten, that's one of the eigenvectors would have been 1, 2, or 2, 1, whichever way it's labeled, so that, right, the proportion is 2 out of 3 and 1 out of 3. So that one is twice as big as the other one, right? Because so the limit as t goes to infinity of the fraction of g of t over the total, just to look at the gap space, well, that's just going to end up being 1/3, the leftover parts. And so in proportion, 2/3 to 1/3 is like 2 to 1. So your eigenvector would have been 2, 1, or 1, 2, whichever way we're labeling things. So anything else I want to say about that? No, that's pretty good. Yeah, that seems. Yeah, I'm up. There's something here that's weird that I need to look at later. So that's pretty much the compartment stuff you all need to know about. There is one last question on this next homework assignment. It talks about a drug being administered to a person. It's got the same sort of idea, right? Where you have kind of a total amount of thing, and it's either here or there. You can draw the compartment model. I don't think in this problem you're losing anything out of the body. You just have exchange between the two. And when you have this exchange between the two, basically you're not losing anything, so the total never changes. So if you figure out what's going on for one of the things, like the adult trees here, you automatically know what's going on for the other thing, the gap, by just subtracting the adult trees from the total. So you can make your life easier and not have to do all the solving all the time. Okay. 105. Let's talk more about where you're going to be going eventually, which is nonlinear differential equations. They're not that bad. They're really not that bad. So I should say, let me back that up. If you are comfortable finding and classifying the equilibria of normal linear systems of differential equations, which we've been doing for the last couple of weeks, meaning if you're comfortable finding eigenvalues and determining if they're positive or negative or imaginary, and then based on that classifying whether you have a source, a sink, a saddle, a spiral that's stable or unstable, or a central one. If you're comfortable with all that, then this next thing isn't that bad. But you have to have already been comfortable with that. I should say, if you're comfortable with that, and also kind of similar to finding the critical points of functions of x and y, like we were doing back at the beginning of the quarter, right? When we were finding whether you had like a max or a min or a saddle on the surface. If you're comfortable with both of those things, then this next thing is nothing new. That's why we did those things first, so then we could do this and already have had the machinery we needed. Let's look at some examples. We already did that example. Let's look at this next one. So I will point out to analyze the stability of the equilibria, there is a graphical method and there is an analytical method. All of your homework questions are on the analytical method. I don't imagine she's going to talk about the graphical method, which honestly is probably good, because it can be relatively confusing to kind of figure out what's going on with the graphical method. So we'll talk about the analytical method first. If you have desire and time, if there isn't need and there's desire and time, we can also talk about the graphical method. But honestly, I don't imagine that is what you all want. But if you do, I'm happy to talk about it. It takes a little bit, it's going to take some mental energy. Let's look at some examples here. Let's say we have the following. So given that dx1 dt is equal to x1 times, they made it easy for us, 10 minus x1 minus 2x2. Oftentimes, this would be given not factored out. It would be given as dx1 dt equal to 10x1 minus x1 squared minus 2x1 x2. and dx2 dt equal to x2 times 10 minus 2x1 minus x2, or normally given at first as dx2 dt equal to 10x2 minus 2x1 x2 minus x2 squared. Given those differential equations, find and classify all equilibria. Which there are going to be 4 of. First, an observation. These equations are symmetric. All that means is that if you interchange x1 and x2, the equations look the same, right? If I swapped x1 and x2, I should say they look the same as each other, right? If I swapped x1 and x2, this would become 10x2 minus x2 squared minus 2 times x2 times x1, which is exactly that equation, and vice versa. If I interchange x1 and x2, I get exactly that equation. When that's the case, it always means that any critical points come in pairs, meaning if 1, 3 is a critical point, 3, 1 also has to be a critical point, because you can swap the x1 and the x2 and still have a solution to the other equation. So all of your critical points are going to come in pairs like that, or they're going to be ones like 5, 5 or 7, 7, where x1 and x2 are the same. It's nice to know that, just because you can kind of be like, okay, I have an idea of what's going to happen here. So to solve this, we're going to do a couple things. Thing one, typically we call the first one of these F. This is F, and this is G. But first, you have to find the critical point. So we're going to set them equal to 0. So x1 times 10 minus x1 minus 2x2 equal to 0. And x2 times 10 minus 2x1 minus x2 equal to 0. There's one easy solution, and I think it should always still be a solution most of the time. 0, 0. If x1 is 0 and x2 is 0, we definitely have 0, 0 as an equilibrium. That's not the only one. We could also set x1 equal to 0. And then this equation is dealt with. But in this equation, let's set x1 equal to 0 and see what happens. So I get x2 times 10 minus 0 minus x2 equal to 0. So I know x2 could be 0, but I've already got that equilibrium. I also could have x2 equal to 10. So I'm going to end up getting x2 equal to 10. So another equilibrium is x1 is 0, x2 is 10. And now, because of what we said before, I'm pretty sure 10, 0 is also going to be equilibrium, but let's find it anyway. So on the other side, we could have over here set x2 equal to 0. And then over here, we'll get x1 times 10 minus x1 equal to 0. So we do get x1 equal to 10. So 10, 0 is also an equilibrium. And now for the hardest one. So basically, we have every way of pairing either factor equal to 0. So you can have this equal to 0 and this equal to 0, or this equal to 0 and that equal to 0, or that equal to 0 and this equal to 0, or that equal to 0 and that equal to 0 at the same time. That's the last one we have to figure out. So we're going to set both 10 minus x1 minus 2x2 equal to 0 and 10 minus 2x1 minus x2 equal to 0. And then we have essentially two equations of lines, and we're going to try and figure out where these lines cross each other. What I'm going to do is solve one of them for x1 or x2 and then plug it into the other one. That's not the only way you can go. You can also try to eliminate stuff. I didn't write them on top of each other, so I don't want to do it that way. So I'm going to solve this for x1. So 10 minus 2x2 equals positive x1. And then we're going to take that and substitute it in for x1 right over there. Then over here, I have 10 minus 2 times 10 minus 2x2 minus x2 equal to 0. Distribute 10 minus 20 plus 4x2 minus x2 equals 0. 4 minus 1 is 3x2. 10 minus 20 is negative 10. Added over there, you get positive 10. So you get x2 equal to 10 thirds. And now we put that back in over here. And 10 minus 2 times 10 thirds is 30 thirds minus 20 thirds, which is also 10 thirds. And that's what x1 is. So our last equilibrium is 10 thirds comma 10 thirds. Cool, we found all the equilibria. Now we have to find the Jacobian matrix, which is just the matrix of partial derivatives. And then we're going to plug each of these equilibrium into the Jacobian and then try and find the eigenvalues to determine or classify whether we have spirals or nodes or whatever. It's a lot of stuff to do, right? It's not like, even though it might be phrased as find and classify the equilibria of this system of equations, that has a lot of machinery built into it, much like solving a system of linear differential equations, right? It's eigenvalues, eigenvectors, the whole shebang. Okay, so let's do the next part. The Jacobian is not too terrible. So as a reminder, and this is actually where I would probably, instead of writing it this factored way, I would probably write it multiplied out, because your Jacobian matrix is your partial of f with respect to x1, your partial of f with respect to x2, your partial of g with respect to x1, your partial of g with respect to x2. I always kind of think of it as f in the top row, g in the bottom row, x1 in the first column, x2 in the second column. That's how I think about which derivatives go where. Although it probably actually doesn't matter if you get them completely wrong. Oh, but then I might need the function I'm trying to take the partial derivatives of. So our Jacobian here is going to be, let's see, so del f del x1 is going to be 10 minus 2x2. Del f del x2 is going to be negative 2x1. And then del g del x1 is going to be negative 2x2. And del g del x2 is going to be 10 minus, oh, I think I missed something in the first part here. I did. In the first part, I should have had a 10 minus 2x1 minus 2x2. And then over here, I should have had a 10 minus 2x1 minus 2x2. Okay. And now we take our Jacobian and we plug in each of our equilibrium. So let's look at 0, 0 first. So j of 0, 0 is going to be 10, 0, 0, 10. Cool. You all already know the answer to what kind of stability we have here. What are my eigenvalues? 10 and 10. So what kind of thing do we have? Well, it's not a spiral because they're not imaginary. So it's either a stable node, an unstable node, or a saddle. Or if you like, if it's either a sink or a source or a saddle. It's an unstable node, right? My lambdas are positive, and so we have an unstable node. The nice thing about a lot of these problems is that often you end up with matrices where you get a 0 in a convenient spot, and your eigenvalues are really easy to see. That's why we talked about it, really, is because of this kind of thing that happens often. Let's look at J of, what was it, 10, 0? Yeah, 10, 0. So plug in 10 for x1 and 0 for x2, I'm going to get 10 minus 20, and then a minus 20, and then a 0. Oh, how convenient. And then a 10 minus 20 again. Yeah, minus 20, so negative 10. So end up with negative 10, negative 20, 0, negative 10. My eigenvalues are both negative 10. So we have a stable node. When you get to something like this, we've already done so much work. No one is expecting you to actually do the work of finding the eigenvalues if it's a 0 there or a 0 there or both. They're expecting you to look and be like, oh yeah, I know what the eigenvalues are. I'm pretty sure it's gonna be the same for 0, 10, but let's double check. If I plug in 0, 10, I'm gonna get 10 minus 20 minus 0, 0, negative 20, and 10 minus 0 minus 20. So yeah, again, same idea. We have lambda equal to negative 10 twice, and we have a stable node once again. And then for the last one, which, yeah, I bet the last one we actually have to work for, so let's give ourselves a new piece of paper. So if I plug in, was 10 thirds, 10 thirds? Yeah, 10 thirds, 10 thirds. J of 10 thirds, 10 thirds. If I plug that in, I get 10 minus 20 thirds minus 20 thirds minus 20 thirds minus 20 thirds. And the same thing down there, 10 minus 20 thirds minus 20 thirds. Ugh. So that's going to equal, 10 is 30 thirds. So I have a minus 10 thirds, a minus 20 thirds, a minus 20 thirds, and a minus 10 thirds. So this is where I really, really, really would not want to actually find the eigenvalues. I could, but it's kind of annoying. We could also do the trace determinant stuff that we've talked about a little bit here. So let me just, we can still find the eigenvalues if you all want, but let me point out how we could do this. The trace is going to be negative 10 thirds plus negative 10 thirds, which is negative 20 thirds. So we know when the trace is negative, you either have stable node, stable spiral, or a saddle. Those are the only options, because the trace corresponds to either the positive or negativeness of your real things, or the positive or negative, or the positive or negative, oh my God, or the positive or negativeness of the real part of your complex eigenvalues. The determinant here is equal to negative 10 thirds times negative 10 thirds minus negative 20 thirds times negative 20 thirds. And that's going to be 100 over 9 minus 400 over 9, which is negative. And really, that's the last word I need to say. It's negative, which means I have a saddle. But it is negative 300 over 9, which is negative 100 over 3. But when the determinant's negative, we know we have a saddle. And the reason that's true is because if the determinant is negative, well, I know it's been a little while since I said this, but another thing that's also true is that the eigenvalues do have to add up to whatever the trace is equal to, and they do have to multiply to whatever the determinant is equal to. And if the determinant's negative, well, then lambda 1 and lambda 2 have to be opposite signs. There isn't any other choice. Or you could go ahead and find them by saying that the eigenvalues are equal to the trace plus or minus the square root of the trace squared minus 4 times the determinant all over 2, if you really wanted to do it that way. I don't, but I mean, it's a matter of preference. Or, and yeah, I know I'm doing all the things, but not everyone wants to see it this way. So let's talk about how you'd actually do it. You could also do it as just saying, I'm going to do the determinant of negative 10 thirds minus lambda, negative 20 thirds, negative 20 thirds, negative 10 thirds minus lambda. And that's going to be that times that. Minus that times that. That ends up being lambda squared plus 10 thirds plus 10 thirds, so plus 20 thirds lambda plus 100 over 9 minus 400 over 9, which is exactly lambda squared plus 20 thirds lambda minus 300 over 9. Hey, look. There's the negative of the trace. there's the determinant. It is not a coincidence. That always happens. I can't factor that. I don't think it factors. But if you wanted to solve it the quadratic formula way, you're going to get exactly that lambda is equal to negative 20/3 plus or minus the square root of 20/3 squared minus 4 times 1 times negative 300/9, all divided by 2. Which is literally the same formula I just wrote down, but writing in the numbers instead. So you kind of can't avoid the quadratic formula here unless you want to, I don't know, see that the saddle is, see the saddle because the determinant is negative. Here, if I simplify this, you get negative 20/3 plus or minus. Oh, you know what I could have done? You know what I should have done? It's not a huge deal, but like a way you could have made your life easier, which I was totally talking about earlier, is let's not deal with fractions. Let's multiply everything by like 3 here. 3 lambda squared plus 20 lambda minus 900/9 equals 0. That's probably a better thing to do. Make your life easier on yourself. So we could have said lambda equals negative 20 plus or minus the square root of 20 squared minus 4 times 3 times negative 100 all over 2 times 3. And then that's going to be negative 20 plus or minus the square root of 400 plus 1200, 1600. So we get negative 20 plus or minus 40. And oh yeah, we do see that we get a negative and a positive. So you have to decide for yourself what the best way for you is to find your eigenvalues or to determine whether your eigenvalues are positive, negative, one of each, or complex. But you have to figure out for you what's going to work the best. Cool. Yeah.
Can you show the quadratic formula with the trace and determinant again?
Yeah, of course.
Thank you.
And then just to be extra super clear here, let me write some things right here, right now, in these last few minutes. If the determinant is negative, you have a saddle. If the determinant is positive, well, a lot of different things can happen. If your eigenvalues are real, meaning the stuff inside the square root is positive. So if the determinant is positive and tau squared minus 4 times delta is also positive, then you either get stable node if tau is positive, unstable node if tau is negative. And then, of course, I didn't leave myself enough room over there, so I'm gonna have to write it over here. It's terrible. On the other hand, if your determinant is positive, but your eigenvalues are complex, so tau squared minus 4 delta is negative, then you have a stable spiral if tau is, holy smokes, I wrote the wrong thing somewhere. I made a small mistake. It's kind of a big deal. I made a mistake right there. It's stable if tau is negative. Sorry. And unstable if tau is positive. Because if tau is negative, then this negative number plus or minus this part here will both be negative, and both your eigenvalues being negative, which means stability. Okay, finally, stable spiral if, again, tau is negative, unstable spiral if tau is positive. So basically, if you don't have a saddle, then tau being negative means you have stability, tau being positive means you have instability. And then depending on the relationship between tau and your determinant determines whether or not you have a spiral of stability or instability or a node of stability or instability. It's kind of neat. Oh, chat. Sorry, I didn't see the chat. When you were determining the equilibrium, how do you determine that x2 equals 10 when x1 equals 0? Good question. Couldn't x2 take on any value? So let's go back and look. Sorry, I missed that earlier. So we look back here. Sorry, if you write something and I don't see it for a while, you're welcome to unmute yourself and say words. Usually I see things, but I didn't then. So if I go back here. So when I set x1 equal to 0, sorry, and let me read your question one more time just to be absolutely clear here. Yeah, so right. So when I set x1 equal to 0, here's the thing. I need both equations to simultaneously equal 0. So if x1 0, this whole equation is 0 for sure. And if x1 0, for this equation to be 0, well, if that's 0, then I either have to have x2 being 0 or x2 being 10. There are no other options if x1 is 0. So, right, because since this equation and that equation both have to equal 0 at the same point. So that's why I'm meaning 0, 0, because this is 0 and this is 0, or 0, 10, because this is 0 and x2 is 10, meaning 10 minus 0 minus 10 will give me 0. It's very, very similar to when we were finding critical points for functions of two variables, and we were setting both the partial with respect to x and the partial with respect to y equal to 0. Cool, good. All right, it's 1:29. Let's call it a day. Tuesday, we'll probably just be talking about, we'll probably do more differential equations or more nonlinear differential equations, unless you all have specific questions you want to come on Tuesday with about the compartment model stuff. But I feel like we fairly well covered the compartment models. Not that I'm not willing to talk about it, just I feel like you should be able to complete the homework assignment based on what we did for compartment models. We never do more non-linear differential equations though, because there are some funky looking ones on your homework assignment. So yeah, we'll do some more examples of nonlinear with maybe some trig functions, maybe some exponential functions, maybe some logarithmic functions, because they definitely are in your homework assignment. So we should do some examples like that. All right, have a lovely weekend. If I don't see you next Tuesday, have a lovely Thanksgiving. I'll see you all the Tuesday after, before your midterm that's on the Wednesday after Thanksgiving, right?